Okay, so as you're working on your lab, hopefully you noticed that if you were to graph the force versus acceleration, you got something linear, and that when you found the slope, you found that it was equal to 1 over the system mass. Okay, and so if we write an equation for this, we're going to say that A is equal to 1 over m for our slope times f, or A equals f over m. And then if you graphed for the second part, acceleration versus mass, you probably got something that looked similar to this. And if you did the inverse of mass, you would have got something like versus 1 over m, something like this. And hopefully you found that the slope, so we use that to symbolize slope, that you found the slope was equal to the applied force. Okay, so that A was equal to F times 1 over m, or again, A equals F over m. And so this represents the relationship between force and acceleration. Sometimes you'll see it like this, and sometimes you'll see it like this. Okay, and we're going to put the net right here, because it's not just the force, but it's actually in reference to the net force, to the combination of all the forces acting on an object. Okay, and so this is Newton's second law, and basically his conclusion is that this is a relationship between applied force and acceleration, and the thing that affects the rate at which something accelerates based on the amount of force is the mass. Okay, so looking at this equation, what happens when there is more mass in the system? Well, it would have less acceleration when there's more mass. Okay, and if there's less mass, there would be more acceleration. So mass is essentially resistance to acceleration. And we mentioned in class that really, if you're in space, the only way for you to determine the mass of something or compare the masses of objects is to shake them or throw them. And this is literally because there's no other way to measure mass. That's what mass is. It's the resistance to acceleration. Okay, we can't really understand it in any other terms. So something with more mass is more difficult to accelerate, whereas something with less mass is easier to accelerate. Okay, and so mass is a measurement of the inertia of an object. Okay, so mass and inertia are two words for the same thing. So an object with more mass is more difficult to move, to accelerate, wants to keep going in a straight line more than something with less mass. And that's what mass is. We can't understand mass in any other way than that. We don't have any other way of describing it other than that. Okay? So let's go ahead and think about this now. We'll try to apply this. Okay, so let's say that I have an object, okay, that is has a mass of 3 kilograms, and it's accelerating at a rate of 2 meters per second squared. Okay, and so the question is, what net force do we have to apply to this object to cause it to accelerate at 2 meters per second squared? Well, we can use the second law equation, that net force equal to m times a. Okay, well, so we plug it in, and we see, okay, 3 times 2, so 3 kilograms times 2 meters per second squared. Okay, and we get that the net force is equal to 6 kilogram meters per second squared. And you might think, well, wait a minute. I thought forces were measured in newtons. I'm given here kilogram meters per second squared. Okay, well, the definition of a newton comes from this net force equation, that 1 newton is the amount of force required to accelerate a 1 kilogram mass at a rate of 1 meter per second squared, which means that 1 newton is equal to 1 kilogram meter per second squared. So these are equivalent units. Okay, so a newton is an example here of a derived unit, and this is what that derivation is, coming from Newton's second law. Okay, so we found this. All right, let's think about another example of this. Let's say we have two objects, one with big mass, and one with little mass, and they are both falling under their weight. Okay, their weight's causing them to fall. So which of these objects has more weight? This one, right? It's bigger, has more mass, which means more weight. Okay, well remember that mass, or weight rather, is equal to m times g. And so this is big M times g. This one has little m times g. So this object is experiencing a smaller force than this larger object here. But we know from previous units that they're going to fall at the same rate. Okay? Well, the reason why, again, comes in Newton's second law. So remember that F net is equal to m times a, or that F net over m is equal to a. Okay? So for this object right here, the net force is its weight, big M times g, divided by its mass, big M, equal to acceleration. Those m's will cancel out, and the acceleration will be equal to g. The reason why this is the case is because even though it experiences a greater force, since it has more mass, it's also more difficult to accelerate. So the same thing will occur right here. Okay? Those m's will cancel out, and we'll get that g is equal to a. Okay, so it'll be the same acceleration for both, even though they have different amounts of force. Okay, this also explains how 9.8 newtons per kilogram strength of the gravitational field is equivalent to 9.8 meters per second squared acceleration from gravity, because if we take a newton and divide out the kilogram, that's what we're left with. Okay? Okay, so now let's go ahead and apply it in the case of a free body diagram. So let's say that we have this 5 kilogram object that's being pulled this way with a force of 40 newtons, experiencing a frictional force back that way of 30 newtons. Okay, so we have a pull this way of 40 newtons. We have a pull back this way of 30 newtons. Okay, we have a weight downward of m times g, or about 50 newtons. And then we have an upward normal force, in this case, also 50 newtons. And again, this is 50 newtons because up and down it's balanced. Okay, but it's getting pulled along a table. And so the question here is, well, what is the acceleration of this block? Okay, well, the way I'm going to do that is by doing net force in this x direction. So I'm going to do an equation for the net force acting in the horizontal direction. So I'll find the sum of the forces acting horizontally. And now this system is not in equilibrium, it's unbalanced. Okay, and so according to Newton's second law, the net force is equal to mass times acceleration. So instead of this being equal to 0, it will now be equal to the total mass times the acceleration. Okay, and then we'll say, okay, we have this force of 40 pulling one way, and we have this force of 30 pulling the other way. Okay, so that gives us 5 kilograms times A is equal to 10 newtons. We'll divide the 5 over and find that the acceleration of this block is 10 over 5 is 2 newtons per kilogram, or remember that kilogram meters per second squared over kilograms going to leave us with 2 meters per second squared as the acceleration of this block. Okay? And that's it. That's Newton's second law. So we're going to kind of go through some more advanced examples so you can kind of get the hang of it. Okay, so the first one we have here is we have a 30 Newton force applied to this system of blocks right here. And each block has less mass, so we have 3 kilograms, 2 kilograms, 1 kilogram. And the question is, what is the total acceleration of this system, and how much force is there between blocks A and B, and how much force between blocks B and C? Okay, well, the net force on this system is going to be 30 newtons. Okay, the total mass of this system is going to be 3 plus 2 plus 1, or 6 kilograms. And the acceleration is what we're solving for. So we divide the 6 over, we get an acceleration for this system of 5 meters per second squared. Okay? Well, if you think about block A, it's getting pushed this way with 30. It's getting pushed this way with some amount. And we don't know. But we do know that block A is experiencing acceleration of 5 meters per second squared. So we can say the mass of A, which is 3 kilograms, times the acceleration of 5 meters per second squared, is going to be equal to the force this way of 30 newtons minus the force between blocks A and B. So if we solve this, we get 15 equals 30 minus that force. So we'll subtract 30 and then multiply everything by -1 and find the force between A and B is equal to 15 newtons. Okay, so 15 newtons of this force goes to accelerating block A, and then after that there's only 15 newtons required to accelerate these other two blocks. Now we can set up a similar equation for B, where it's pushing 15 this way and solve for this, or we can just say, well, if all of these are accelerating at 5 meters per second squared, how much force would be needed to accelerate block C? We can say, okay, block C has a mass of 1 kilogram, okay, times its acceleration of 5 meters per second squared, and then we can say, okay, well 1 times 5 gives us a force of 5 newtons. So the force between blocks B and C would be equal to 5 newtons. The force between A and B is equal to 15 newtons. And the acceleration of the whole system is 5 meters per second squared. Okay, and I know that I went fast, and that might be kind of confusing, but at the end of the day, each piece of mass needs a certain amount of force to accelerate it. This whole system is accelerating together. So let's look at this one too. The question here is how much friction between these two blocks, and what's the acceleration of this system, or how much friction is required to keep these blocks from slipping, we'll say. Okay, the net force on this system is 30 newtons. It's having to accelerate 6 kilograms of mass, and we want to solve for A. So again, here we get acceleration of 5 meters per second squared. Okay, and so this whole system is accelerating at 5 meters per second squared. If you think about it, 25 of those newtons is going to accelerate that, and the rest is accelerating that. So this block right here, if we do a free body diagram, we have a push this way of 30 newtons and an unknown push this way. Okay, so what we can do is we can say again, F net equals m times A. Okay, so the mass of block A is 5 kilograms times the acceleration of 5 meters per second squared. It's going to be equal to the 30 newtons minus that missing force of friction. That will give us 25 newtons here equals 30 newtons minus this unknown force, so that the unknown force turns out to be 5 newtons. Okay, you can also look at it from the perspective of that block. It has a mass of 1 kilogram. It needs to be accelerated at a rate of 5 meters per second squared, and so the force acting on it would be 5 newtons.